Now let's see this problem where it involves again moles and equations. It says, consider the following reaction. We have magnesium sulfate reacting with barium chloride, and we have those two products, magnesium chloride and barium sulfate. The first part says, if we start with 10 grams of magnesium sulfate, so we have 10 grams of this. If we start with 10 grams of magnesium sulfate, how much barium chloride is needed to react with it exactly? Okay, so this is the type of reaction we've seen, the type of work that we've seen last week. First of all, the equation is balanced already, yeah? So we see that these things react in ratios 1 to 1 mole to 1 mole to 1 mole. Great. So we just need to find out how many moles of magnesium sulfate are the 10 grams that we have here. So whatever moles we find, the same ratio of moles will apply to others, to all the others, reactants or products. So, okay, so magnesium sulfate, I have found here its relative, I have found the relative formula masses of all of them to save us time. So magnesium sulfate here, I have a 120, that its relative formula mass is 120, and the barium chloride is 208, although we don't need it. And this one is magnesium chloride is 95,3. Okay, say 95. This we're going to need, the 95. And barium sulfate, again, we're not going to need, but nevertheless, it's 233,4. Let's leave it round number, 233. All right. So what do we have here? We have that if we concentrate on the magnesium sulfate, 1 mole of magnesium sulfate is its relative formula mass in grams. So that 1 mole, in other words, corresponds to 120 grams of magnesium sulfate. Now that we have 10 grams of magnesium sulfate, how many moles is that? And we take the ratio, and we find that the moles, in other words, the X, is 10 grams divided by 120 grams, and this will be moles. Yeah, and this, how much will it give us? I find here 0,083 moles. Of course, I have rounded up the numbers. I don't know if it's exactly 0,083, but I mean something like that we find. Mole. Okay, so in other words, the 10 grams that I have available and which react are actually 0,083 moles. So this is 0,083 moles. And because the ratios of everything here is 1 to 1 to 1 to 1, it means that this is also 0,083 moles. Because this is what I need to find, the mass of magnesium chloride. So that is why I'm writing here that just the moles of magnesium chloride. So now that I know how many moles of magnesium chloride are produced, I can find how what mass it corresponds. So what am I saying here? I know that 1 mole of magnesium chloride has a mass of 95 grams. 1 mole of magnesium chloride has a mass of 95 grams. Come on, 95 grams. Now that I have this number of moles, how many grams are they? 0,083 moles of magnesium chloride. How many grams is that? And this is my answer to question A. So from here, if I solve for X, I mean, this is a ratio, of course. Remember these ratios, I hope you can do that. Eh? This X is 95 grams times in this inversed, which is 0,083 moles divided by 1 mole. And so in other words, this is 95 times 0,083, and this answer is grams. And according to these calculations here, I find 17,3. All right. What? Oh, sorry. Oh my goodness. Of course. Sorry, if not, it's the mistake I made. If we start with 10 grams of magnesium sulfate, how much barium chloride, not magnesium chloride, barium chloride is necessary? Oh my God, sorry guys, so sorry. So it's this that we need to find the mass, not this one. Yeah, sorry about this mistake. It's how much barium chloride is needed to react with it exactly. So this is the mass that I'm looking for, which is 208. The formula mass, the relative formula mass of barium chloride is 208. So this is the 0,083 moles that I need to find. Oh my God. So let me remove all that because so barium, 1 mole of barium chloride, 1 mole of barium chloride has a mass of 208 grams, 208 grams. And now we can find the 0,083 moles. How many grams is that? So this should be here. Correct mass of the 208 of barium chloride. So this is 208. So if I solve here for x, it's 208 grams times this inverse 0,83 divided by 1 mole. And this is now, okay, I hope this is correct. Oh, 17,3 I find. 17,3 grams. So in other words, the 0,083 moles of barium chloride have a mass of 17,3 grams. Okay, let me remove that because this was not necessary. Okay. Okay, so if we start with 10 grams of magnesium sulfate, how much barium chloride is needed? We need 17,3 grams. Guys, did you understand that? Because I made a mess and might have confused you gravely. Sorry, it was we had to work with a barium chloride, not a magnesium chloride. Okay, so this is the mass. The next question says, what theoretical yield of barium sulfate should we expect? All right. How much, in theory, in other words, if we start with these quantities of magnesium sulfate and we also found the quantity of barium chloride necessary, how much would we expect, how many grams of barium sulfate would we expect in theory? So let's see that in part B. So now we need to find out how much barium sulfate we should expect for this reaction to yield in theory. So we know that we should expect, first of all, we have moles, 0,083 moles of barium sulfate. And if 1 mole of barium sulfate has weighs 233 grams, how many grams of are the 0,083 moles of barium sulfate? So 1 mole of barium sulfate has a mass of 233 grams. In our case, that we have 0,083 moles, 0,083 moles of barium sulfate. How many grams is that? And that would give us the theoretical value, the theoretical yield of barium sulfate that we should expect in theory. So that would be now 233 grams times this this ratio here inverse. So 0,083 moles divided by 1. And this is 233 times 0,83 is 19,37, which means about 19. This is about 19 grams. Okay, maybe write the decimals, why not? 19,37 grams, I find. This is the mass of, the expected mass of barium sulfate, of barium sulfate. The theoretical mass that we expect if we start with 10 grams of magnesium sulfate. All right, so this is what we found here, 19,37 grams. If we only get 15 grams of barium sulfate, what is the percentage yield? Okay, so we do the experiment, in other words, we do the reaction with the real products, and we find that we get 15 grams instead of 19,37. What is the percentage yield? So let's do the last part. So in the last part we have, remember the percentage yield is what the actual yield, what we actually get. In this case we got 15 grams. And what did we expect to get in theory? We expected like 19,37 grams. And of course we have to multiply by 100 to get the percentage yield. And what this is 77,44. So this is the percentage yield that we get, all right? So to find the percentage yield is actually easy. Remember, it's the ratio of what we actually get, the actual yield, divided by the theoretical yield, the calculated, the one that we get from our calculations. And we'll multiply by 100, of course, to get the percentage. And in this case, we get that only 77,4% of what we of the expected value. This is the percentage yield of this reaction. All right. Now, another thing that we need to discuss is how about if one of the products now it's a gas? Because when we have a gas involved in our reaction, so like for example in this reaction we have an iron oxide reacting with carbon monoxide, and the result is iron and carbon dioxide. So we see there are some gases involved here. In the previous reactions that we've done up to now, we did not discuss at all about volumes of gases, and they were not gases, the ones that the items involved in the reaction. But look at this reaction. We have a gas here, which is the carbon monoxide, and we have also this gas, carbon dioxide, which is one of the products. Now, but there is nothing special about this, nothing difficult. The only thing that it's actually an easy thing to know, an interesting thing to know, and that will make our life easier, is that 1 mole of any gas, 1 mole of any gas at room temperature and pressure occupies a volume of 24 cubic decimeters. It's like a standard. So apart from, up to now we know that 1 mole of anything has a certain number of particles, which is the Avogadro number. Now, when it comes to gases, apart from this number of particles, which still applies, apart from the Avogadro's constant, in other words, 1 mole of any gas also occupies 24 cubic decimeters of volume always. So whenever we have a gas, we know that 1 mole of this gas will occupy this volume. So it's another extra piece of information which makes our life a lot easier if to find out quantities involved in chemical reactions. So in other words, okay, let's do this problem that involves this equation. It says we are given now this equation, it's already balanced, and they ask us to determine the volume of carbon dioxide gas produced, here is the product, produced from 112.5 grams of iron. What they mean here, what is the volume of gas produced in this reaction if the volume of iron produced is 112.5 grams. In other words, the volume that corresponds to this mass of iron produced at room temperature and pressure. When we say room temperature, they mean the 25 degrees Celsius. We take it as 25 degrees Celsius. And pressure is the atmospheric pressure. We can take it roughly as 10 to the 5th Pascal. The normal atmospheric pressure, in other words, because chemical reactions usually, very often, in fact, happen at atmospheric pressure in the lab. All right, so remember, this 24 cubic decimeters correspond to room temperature, not 0 degrees Celsius, but 25 degrees Celsius, because if it was at 0 degrees Celsius, it's a little bit less, it's 22.4 only. But in chemistry, we are going to use the 25 degrees Celsius, in which case 1 mole occupies this volume, 1 mole of any gas, that is 24 cubic decimeters. It also worth to say that very often, volumes of gases, generally volumes, will be given in cubic centimeters rather than cubic decimeters. And it's good to remember that to know the correlation between cubic decimeters and cubic centimeters to be able to convert to one another. So it's good to know that 1 cubic decimeter is actually 1,000 cubic centimeters. So if they give us a volume in cubic centimeters, we simply convert it to cubic centimeters by dividing the value that we have with 1,000. But nevertheless, this we can see it. We'll see it many times from now on, because we're going to see it very often when we talk about concentration of solutions, which is the next topic that we need to get to. All right, so let us go back to this reaction now. We need to find the volume of carbon dioxide produced if the product of iron is 112.5 grams. So they give us mass for the iron because it's a solid, and we need to find the volume of the gas. And what can we do here? We have the reaction which is already balanced. We see that if we look at the moles reacting here, it's 1 to 3 to 2 to 3 moles. This is the ratio of moles that react. So obviously, since we start from the ion that is produced and we know its mass, it's good to know how many moles of iron this mass represents, so that we are able to find the moles of carbon dioxide involved here, the actual moles of carbon dioxide produced. All right, so we know, okay, iron here, 1 mole of iron, I mean, from the periodic table, the relative atomic mass of iron, or rather, this is the symbol that we use here, is for iron, if in the periodic table is 56. Okay, if we look in the periodic table. So, which means now 1 mole of iron, this is for iron, 1 mole of iron, in other words, has a mass of 56 grams. Now, the 112.5 grams that we have in our case, 112.5 grams, how many moles is that? Ratio, solving for x. So this will be 112,5 divided by 56 and times 1 mole. So obviously this answer will be mole in moles, and this is equal. It's about 112, 2.7. We can take it as 2 to make it round. Okay, let's take it as 2, round number, so it makes our life easier. So we see that this mass that we are given of iron is actually 2 moles, which is very nice because look at this, 2 moles. Because we know that 2 moles now correspond to 3 moles of carbon dioxide from the actual reaction, 2 to 3, isn't it? The ratio given by this reaction, determined by this reaction, is 2 to 3. So we know that if 2 moles of iron are produced, the moles of carbon dioxide produced are 3 moles, because look at this, 2 moles to 3. So we know that we have 3 moles of carbon dioxide produced. And since 1 mole of carbon dioxide has a volume of 24 cubic decimeters, because 1 mole of any gas has this volume, that means the 3 moles of carbon dioxide have a volume of 3 times 24 cubic decimeters, isn't it? And well, this is 72 cubic decimeters. So the answer is that the volume of carbon dioxide produced is 72 cubic decimeters. This is the volume of carbon dioxide produced. Okay. Let me show you. I found a problem in a past exam paper from spring 18. I think it is. Remember, I think it is from spring 2018. Let us try this one. Actually, it's this part here which involves some calculations. The other are actually like definitions and easy questions. Let's see this. Let's make it a little bit bigger. Let's see this example. You see, in the exam, the problems appear quite a lot easier. We have a 0,095 grams sample of a gaseous element Y. It's an element. The gaseous element Y occupies a volume of 60 cubic centimeters at room temperature and pressure, in other words, at RTP conditions. Determine the number of moles of element Y in 60 cubic centimeters. We see that we don't know what element it is, but we know that it's a gas, because it's a gaseous element. And since it's a gaseous element and occupies a volume of 60 cubic centimeters, we can find how many moles of this element we have, isn't it? So we know that 1 mole of any gas occupies a volume of 24 cubic decimeters, which here we are given cubic centimeters. We could change that to cubic centimeters, or vice versa, it doesn't matter. Or we can write it in the form of 24,000 cubic centimeters, just because they give us the volume of in cubic centimeters. Now, anyway, so 1 mole of any gas, of this, in our case of gas Y, occupies this volume. Now that we have 60 cubic centimeters of this element, how many moles is that? How many moles is that? and we can take the ratio, and we can find that the number of moles is 60 divided by 24,000. 24,000. And this is, what is this now? 0,0025 moles. So we found how many moles of this element, the gaseous element Y, we have. Determine the number of moles. Oh, here is the number of moles. So we found it. So you see, we didn't even have to know what element it was. Oh, here we place our answer, 0,0025. All right. Now calculate the relative molecular mass of element Y and hence suggest the identity of the element Y. Okay, because they give us a mass here. All right. So we know that this number of moles corresponds to this mass. So we have that 0,0025 moles of this element Y has a mass of 0,095 grams. Okay, so 1 mole, how many grams is that? All right, so this X here, hold it, let me find quickly my calculation. What I find that this X is 38 grams, which means now, but be careful now, that this is the element Y. It's an element, gaseous element. Now, when I look in the periodic table, I mean, there's no atom that has this mass of 38, atomic mass number of 38. But remember, this is an element. So obviously, the element Y, it's obviously it's a molecule that has, usually molecules are made out of 2 atoms, isn't it? So now look at this. If this is a molecule because it's an element, obviously, what is half of that? It's 14 grams. So if it's, I think that this is nitrogen because relative molecular mass is, so we find 38 grams. The identity of the element, I would say this is nitrogen because nitrogen has an atomic number of 14. You see, the relative atomic mass of nitrogen is 14. So the element nitrogen would appear in this form, isn't it? And that is why it justifies why its relative molecular mass has the value of 38. Okay, so I hope you agree with me, but now we have come to the end again of this session.